All right, so we're going to look at an alternative form or version of the chain rule, which uses Leibniz notation. And here it is. It says the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. And really, this is just coming from our original form of the chain rule, where we're saying y is equal to this composite function. So we're letting y equal f of u of x. So if we kind of write this alternative, just to kind of see how everything matches up, if we write this alternate form down below, dy dx is equal to dy du times du dx, kind of see how things match up. So this u prime of x, this is really just the derivative of u with respect to x. Over here, if we're letting y equal this term inside the brackets, y equal to f of u of x, well then differentiating is just the derivative of y with respect to x. So this du dx, this is our derivative of our inner function. The dy dx, that's just the derivative we're trying to calculate. And like we said, this is our derivative of our inner function. And this dy du, that's the derivative of our outer function. So we can kind of view, when we think of y in terms of these two functions, f of u of x, we could think of y as a function of x, but we can also, if we just kind of consolidate this inner function, we can also think of y as just a function of u, just the outer function part. So, and that's what we're capturing here. This is the derivative of just that outer function. And we're differentiating with respect to u. All right, so there's kind of two ways to think of variable y here. If we kind of rename this as y, we could think of y as a function of x. Or if we kind of just consolidate that inner function and just call it u, we can think of y as just a function of u. So there's this kind of two different versions of, or two different versions of y. And so we can differentiate y with respect to x. This is really what we're after. And what we can do is we can differentiate y with respect to that inner function u, and then multiply that result by the derivative of the inner function. So it's just another way to represent our kind of an alternate form for our chain rule. And let's just try an example with this, just to see how we might use this other form. So let's use the chain rule to calculate dy dx, where y is a function of u raised to the power 5 minus 2 times u cubed plus 8. And then on top of this, u is a function of x. So u is equal to x squared plus 1. So just to kind of think about what's happening here, what this equation is showing us is that y actually is a function of u. That's how it's written. It's written as a function of u. Now, over here, u, in turn, is written as a function of x. And so sort of indirectly, if u is a function of x and y is a function in terms of u, indirectly then y is a function of x as well. Y can be thought of as a function of x as well. All right, so if we change x, that's going to change our function u. And if we change x, that's going to change our function u, which is going to change our variable u here, which will ultimately change our function y. So kind of we have this indirectly, if x varies, it's going to change y. So y actually is a function of x, indirectly. And so it makes sense then to talk about, well, how does function y change as we make changes to variable x? So that's what dy dx really measures is, well, how is your function changing as x changes? And so the way we kind of investigate that is with chain rule. So our chain rule says the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. All right, so let's calculate derivative of y with respect to u. And we can do that. It's 5u to the power 4 minus 6u squared. Not too bad. And then let's multiply that by the derivative of u with respect to x. So derivative of u, just differentiate this. We get 2x, and then derivative of 1 is 0. And now when we're looking at this thing, we kind of have some u terms here. We have some x's here. And we want to be consistent with our variables. And so if we look at the derivative that we're actually trying to calculate here, it's the derivative of y with respect to x. So this x here is telling us really the variable we're interested in is x. So we're interested in variable x. So what that means for our purposes is we want to replace all of these u's. We should replace them with x's. And the way we do that is we know what u actually is. It's x squared plus 1. So wherever we see a u here, we're just going to replace it with x squared plus 1. So we have a u here, we have a u here. We're just going to replace each of those with an x squared plus 1. So let's actually see how this is going to look. And we'll throw it in up here. Why not? So it'll be 5. And then instead of u to the power 4, it's going to be x squared plus 1 to the power 4. And then we have a minus 6. And then instead of u squared, it's going to be x squared plus 1 squared. And then we have this multiplication by 2x at the end. And so this is just another kind of situation where we might need to use chain rule, where we're kind of presented with these apparently two different functions, but it turns out one of the functions is kind of indirectly a function of the other variable. So what we're seeing here, y is a function of u, but then u is a function of x. So indirectly, really y is also can also be thought of as a function of x. All right, so that's going to do it for our chain rule discussion. So definitely one of our important derivative rules that we're going to look at here. So it definitely helps to practice this over and over again. The more you do these, the stronger you'll be able to do on our homework and exams. So really just keep practicing these examples. And then in the next lesson, we're going to learn a kind of a new differentiation technique. We're going to kind of investigate some techniques for differentiation. And so that'll be next. Implicit differentiation, actually. I think that's next. So we'll see you there. Bye-bye.